All right, so I am Jean. I am a grad student at Caltech, 4th year now. I'm going to be talking about our efforts to find TDEs in the radio, which, as you've heard, is very hard, but we're trying our best. And of course, I've had many collaborators in this effort, primarily the BLAST team and the ZTF-TDE team, many members who are here. So thanks to all of you. Let's get started. So first, for a quick outline, I'll start by giving a little bit of background. You've already heard a lot of it, so I'll go pretty quickly. And try to motivate radio-selected TDE searches, why we want to do this rather than just do follow-up like we've heard about already. I'll talk about what we found in the searches, some results, the lessons we've learned, and what really needs to happen. So you've seen some of the multi-wavelength signatures of TDEs. Just to review, some of the original predictions for TDEs suggested we'd see them in the X-ray and, of course, EUV, which is not going to be observed, but this emission will come from some shocking stellar debris or an accretion disk. Some of that emission might be reprocessed into the optical in UV, and this green, I have this here, this green and red light curve here is an optical light curve for one TDE. You also can heat up dust in the circumnuclear medium surrounding the TDE. That'll produce an IR light curve, and this blue and orange light curve here are mid-infrared emission from a TDE. And so this tends to be on a longer time scale than the optical emission. Of course, most interested in radio emission. I must say it's really great to have 2 radio TDE talks in a row. I've never seen that before. So just to review a little bit about what you've already heard, there's a number of different possibilities for how TDEs could produce radio emission. I put a little cartoon here to show some options. So you might have some outflowing stellar debris slamming into the circumnuclear medium. You might have a wind or a jet launched from an accretion disk slamming into the circumnuclear medium, or maybe some internal emission producing radio emission. And so this has been observed in a number of TDEs. I've shown sort of a subset of the TDEs you saw in the previous talk in this radio light curve plot here. So this is time since this roughly like the optical peak or whatever you define as the start time of the TDE versus radioluminosity. These solid blue lines up here, the thin ones, are examples of these jetted TDEs, which tend to be very bright. And then you see these dashed blue lines down here, which are non-relativistic TDEs. They tend to be maybe an order of magnitude or so fainter than the jetted TDEs. And I've also shown in bold some examples of radio-selected TDE candidates that I will talk more about later, but you can see they have a huge range of emission. They're spanning the luminosity range from these very jetted TDEs to the non-relativistic TDEs, but I'll discuss them in a lot more detail. And so there's a number of open questions about radio emission from TDEs and related topics. So of course, first, how do TDEs produce radio emission, which you've heard quite a bit about? Is there some dichotomy between events that launch maybe outflows, accretion disk winds, and jets, such as the on-axis jets we've seen from some really extreme events? Also, how does TDE emission depend on the nuclear region? You saw that many of the radio emission mechanisms require things to slam into dust. So if you have more dust in the vicinity of the TDE, you might expect more radio emission. You might also expect more IR emission from heated dust, maybe less optical emission because of extinction. So there should be some sort of correlations between what the nuclear region looks like and what the emission looks like. And then this was sort of hinted at by one of the questions earlier, but most known TDEs are selected in the optical and X-ray and some IR. Are we missing TDEs? Are there TDEs that don't produce optical, X-ray, or IR emission that you won't see unless maybe you look in the radio or something? And so these are the open questions that I'm going to sort of focus on for the rest of this talk. So now I'll switch into sort of an overview of how we observe TDEs in the radio, why we want to look at radio-selected TDEs, and sort of the landscape of radio-selected TDEs we found so far. I'll discuss what we've learned. I'm also going to highlight just a pending results that's sort of cool. I'll talk about that later. And then I'll discuss some next steps. So first, an overview of radio observations of TDEs. So I wanted to start by summarizing the different tactics people have taken to detect TDEs in the radio and talk about some of the pros and cons of each and the differences between them. And so, of course, you've already heard a lot about follow-up of known TDEs. I think you'll hear more about it later in this conference. In this case, you take a TDE you found in, say, the optical or X-ray. You point the VLA at it. You can decide when you point the VLA at it, at some level, of course. You can decide what sensitivity you want. You can decide what time scale of observations you want, what frequencies you want. So you have a lot of possibilities for detecting certain types of emission. You can have these beautiful light curves like this shown here, which is a 15 gigahertz light curve for one TDE. But of course, you will also be limited. You're going to be limited by the availability of telescopes and human decisions on prioritization, you can't observe every TDE, you have to make a decision somehow. You're also limited by selection effects in the discovery method. If not all TDEs produce optical emission and you're only observing optical TDEs, you're going to miss a lot of potentially very radio bright TDEs. Another option is to take radio surveys, so maybe the VLA has observed most of the sky multiple times, take that data and just look at the positions of known TDEs to try to set constraints in a more unbiased way. You don't have to pick specific events anymore. In this case, you can just look at every TDE in the footprint. You can sometimes get very lucky with timing. Maybe you'll get, maybe a radio survey has observed your TDE right after it started. Maybe it happened to pick up a rebrightening. So there was a ATEL that was put out fairly recently for the TDE Assassin 15OI, where the VAST survey detected rebrightening that, as far as I know, no one was actively following this up and found that separately. It was only discovered by chance, so you can't get lucky. Again, you're still limited by selection effects in your discovery method. And also, one problem with using radio surveys is the sensitivity, timescale of the observations, and the frequency of observation is predetermined. So that's going to sort of set what sort of emission you can detect from these TDEs. And of course, option 3, which is what I've been focusing on, blind searches in radio surveys. So in this case, you don't take a known TDE. You start with a radio survey and you look for, say, every radio transient at the center of a galaxy that somewhat looks like what you've seen from previous TDEs. This doesn't require necessarily that there be an optical or X-ray flare. Of course, if there isn't, it's harder to actually say something is a TDE, but you can still try. You can sort of compute a completeness. You can try to compute radioluminosity functions. So it gives you a lot of benefits in terms of finding new types of candidates you wouldn't otherwise know about. Of course, as I said, it's difficult to confirm candidates, and it can be very difficult to find multi-wavelength counterparts. Radio emission from TDEs is very long timescale. A lot of these optical surveys haven't been on for very long. So we may be finding radio-selected TDEs that had optical flares. There was just no coverage at the time. But over the next decade or so, this problem should be a little bit better. And so now I want to sort of summarize all the radio-selected TDEs we found so far, what they look like. There's not a huge number yet, but we're getting up there quite rapidly. And so I wanted to start by talking about how this process actually occurs. How do you find a TDE in the radio? And so I wanted to summarize the VLA Sky Survey as an example of this, because most radio-selected TDEs have been found with VLAS or its predecessors, and so it gives a good sort of picture of what this might look like. So VLAS is a 3 gigahertz radio survey. It's fairly sensitive with fairly high resolution, which is good for finding TDEs because you want to be able to say where they are in the sky to pretty good precision. It's observed in 3 epochs with a roughly 3-year cadence, and it's observed with VLA. Pretty picture up here. One thing that's important to keep in mind is based on the survey parameters, you're going to tend to be sensitive to TDEs that are peaking on roughly a 3-year timescale if you're looking for things that turned on like between 2 VLAS epochs. Because the cadence is 3 years, you're going to be sensitive to things that tend to evolve on 3 years. If you compare VLAS to an older radio survey, one of its predecessors, you might get longer timescales. And you're going to tend to be sensitive to things that are brightest at 3 gigahertz for a fairly long, around a 3-year timescale. Based on the sensitivity of VLAS, you can detect jetted TDEs out to at least a gigaparsec or so, and non-jetted TDEs out to a few hundred megaparsecs, depending on exactly what luminosity you assume. And so we've done a lot of work, and others have done a lot of work taking this data and trying to find TDEs, and so this is an example of how you can do it. So Dylan Dong, who's a Jansky Fellow at the NRAO, has put together a catalog of all sources that were not detected in the first epoch of VLAS and then turned on 3 years later. So this is an example of one where this is a 2018 observation from VLAS. This is a 2020 observation from VLAS, separated by a few years. And you see this little bright source turn on. With this catalog, we now want to narrow down to TDE candidates, which is the challenging part. So right now, we're starting with a fairly simple selection. And this is generally in the past how I think people have done this. You take a radio transient that's in the center of a galaxy. So in this case, this transient is in the center of this galaxy in Pan-STARRS. We throw out anything that has past variability in really any survey. Any evidence for AGN activity, we get optical spectra for everything, and throw out things with any broad line emission and sometimes any narrow line emission if it's very clearly AGN-like. We require that they be relatively nearby, which means we might miss some of the on-axis jetted events, which are more rare, but others, I think, have extended this, and we are looking at higher redshift things. And so after all the selection, you get some candidates, which some people might argue low-level AGN activity could cause some of them, but we delve into more detail for most. And so this is an example of one. And this one is sort of fun. The reason I like to show it is because the legacy survey and the optical took another image of this during the TDE, and so you can see the bright optical flare that happened at the same time, or a few years before the radio flare. So it's just pretty. But yeah, so that's what a radio-selected TDE candidate might look like. And so there's been a number of different efforts to do this, and they've resulted in a wide range of candidates with different properties. So I'm going to start by talking about a few that were radio only, and then later I'll talk about some candidates with multi-wavelength counterparts. So these were the first really 3 radio-selected TDEs. Maybe there's one other before this. Were all radio only. They weren't found between 2 epochs of VLAS. They tended to be found between VLAS and a much earlier survey, so they tend to have longer timescale emission. So I've added their light curves to this sort of same plot you've been seeing of time versus radioluminosity. So these thin lines are the same ones you saw before, but now I've added these 3 thicker lines, which are the radio-selected TDEs. You can already see they span the full range from very luminous, long timescale emission, sort of consistent with these jetted TDEs, down to very faint emission from non-relativistic TDEs. And so this is work by Vikram, Hannah involved, Maren Anderson, and then myself. And so we're already seeing with only these 3 events, they span the full range of luminosity and energetics from other radio-detected TDEs. They're sort of all over the place. We don't have any strong optical UV or IR counterparts from archival data. Of course, this is one case where these could be so old, like this one is decades old. I think this one's also decades old, where there might just not be coverage at the time of a flare. So we can't say 100% there was nothing there. With VLAS, we've extended this sample using our search between VLAS Epoch 1 and Epoch 2, so shorter timescale things. So we have, I say greater than 30, it's much larger than that. We're just still getting optical spectra to rule out AGN, or we're still reducing the optical spectra. I think we have all of them now. But so I've put an example of radio luminosities for some of the ones where we have optical spectrum. You see they're just all over the place. We see luminosities spanning the range from jetted to non-relativistic. The large majority of these are radio only. Again, the different timescales of the emission could play a role in this. Roughly 20% have optical and or IR counterparts. I'll talk about a few of those later. And so from these radio-only sort of TDEs, we're already finding that we're spanning this huge range in luminosities. We're not seeing any evidence for a dichotomy, a clear dichotomy. Of course, we have a lot more data we need to analyze to be sure, but no clear dichotomy between non-relativistic and jetted TDEs. The energetics span the full range. And we are finding things that might not have multi-wavelength counterparts. So these would not be found with other surveys. Of course, maybe they're just too old, but it's still suggestive. And so then we can move to things with multi-wavelength counterparts where it's a little bit easier to say something about what actually is going on. And so one of the earliest VLAS selected TDEs was J1548, which we published a couple of years ago, which is a IR luminous TDE that launched something like a non-relativistic outflow. And so this plot here shows time on the x-axis and IR luminosity. So this is integrated over the WISE mid-infrared bands. And you can see this very slow turn on over a few years that reached 0.1 Eddington. So this is a very luminous IR flare. There was no optical flare to the limits of at least ZTF and Atlas and every other survey we could find from the time. And at the same time, I've added the radio light curve to this plot here, so you can see it getting brighter. It's this little green one down here. So the radio emission turned on. The radio SED is very unusual. You sort of heard about some suggestions for inhomogeneous media causing weird radio emission. We definitely see that here. The radio SED has multiple peaks. It's not a synchrotron spectrum. But I think the most exciting part about this is it's not discoverable with optical surveys. There's loads of dust. Maybe this suggests that radio surveys are going to find things in dustier galaxies. This wouldn't be too surprising. But we're definitely going to be finding things distinct from what is going to be discovered from, say, prompt follow-up of optically selected TDEs. And we can continue pushing on this sort of trend of what is maybe different about the radio-selected TDEs. And so we recently published a sample of radio-selected TDEs that had optical flares. One thing to note is that most of these were not previously known. So we had 6 events. There are more that we found in later epochs of VLAS, but this is sort of the initial sample of 6. It's going to be fairly incomplete, again, because of this timescale issue, where many of the optical flares probably occurred before ZTF turned on, but we still have a few. The black light curves here show the radio emission. They're sort of spanning this full range from non-relativistic to jetted in terms of energetics and luminosity. We see a huge differences in behavior. I can give you much more detail about these if you like at some point during this conference. One thing that's sort of interesting is we do also see a possible trend towards lower black hole masses with only 6 events. It's hard to say exactly whether that's definite, but it's sort of a tentative trend. We also can compare the optical flares of these events to the optical flares from the optically selected TDEs. So in this plot here, we have blackbody luminosity measured from just integrating over the optical light curve on the y-axis and blackbody temperature on the x-axis. These are both measured at peak. The colorful points, the colorful weird shaped points, are all the radio-selected TDEs, and these blue points are the ZTF-selected TDEs from Yuhan's sample. We see a tentative trend where the radio-selected ones have cooler, fainter optical flares. Again, sort of suggested that maybe dust is playing a role here. We also see long-lived spectral features. So this is an H-alpha light curve for 2 of our events, the colorful points here. And then I would focus on these black upper limits and these black light curves here. These are for optically selected TDEs. You can see our events have rising, brightening H-alpha emission, whereas all of the optically selected TDEs really have fading or non-detected H-alpha emission at such late times. So we argue that these emission lines are suggestive of lots of dense cold gas near the black hole. And so we sort of concluded that radio-selected TDEs may probe populations that have more dense cold gas near the black hole than is found by, say, optical surveys. And they may also be associated with lower mass black holes than can be found with optical surveys. Okay, and so then going back to the questions posed initially, we can try to push on them a little bit. Of course, we don't have answers. So question 1 was, what is the origin of radio emission? We have a lot more work to do on this with the VLAS sample. We have a lot of radio follow-up that still needs to be analyzed. But so far, just based on the luminosities we're seeing in some energetics arguments, we don't see an obvious dichotomy between very clearly jetted and very clearly non-jetted events. Of course, these are all detected at late times, so even if they're jetted, the outflows have expanded and slowed down a bit, so it can be a bit hard to tell, but we have a lot of data still to process. So there are a lot of next steps, including analyzing our full sample, and of course, I think systematic radio follow-up of known TDEs, like being done by people here, is really, really useful. It'd be nice to extend this to broadened optical samples, so I'll mention this a bit later, but with ZTF, we're trying to expand the definition of a TDE. It'd be nice to see if we could push on some of those with the radio. Maybe they'll look more like some of the radio-selected events if we, say, allow TDEs to be redder than it's currently done. I also just want to mention this hostless TDE candidate, which is also starting to push on this question of where the radio emission is coming from. So this is a radio-selected TDE in the cosmos field, so using old cosmos data. So this is a 2004 very, very deep radio image at 1.4 gigahertz. This is 2018, and so you can see the source disappears. These are different scales. I've scaled everything to the beam size of the image. But so this is a 100 microjansky source that disappeared over a decade. And there's no host in 28th mag HST imaging. There's no host in any other imaging of the cosmos field, and it's more than 10 effective radii from every nearby source. So this is an event from a very small low-mass galaxy maybe, or an IMBH type thing, that's managed to launch a quite luminous radio source. Sort of looks like a TDE. We can try to say a little bit about what triggered it. It's hard when you don't have a host. So it could be something like, so this is a radio luminosity versus timescale for a few different types of events. And this box sort of shows the range where this event might lie. You can see it starts to get up to TDE-like luminosities and timescales. Maybe if this is a lower mass black hole, you'd expect it to be a bit fainter. It could also be a long DRB or some weird exotic neutron star merger type thing, but it's pretty cool, so keep your eye out for that. We've also seen that the nuclear environment plays a role. So we're finding a lot of dust, but I think what we really need to understand is first, can we push the limits of the optical selection and see similar events using different surveys? Maybe do some dedicated radio follow-up of dustier candidates. And it also, something we're working on that I think would be really useful is have more predictions for multi-wavelength emission as a function of dust. You know, what IR emission do you expect to see, what radio emission as you change the amount of dust near a black hole, making some simple assumptions. And then are we missing TDEs? Seems possible, but there's a lot of work we can do to try to push on them with radio surveys and understand what we might be missing better. And I suspect I'm out of time. 20 seconds, okay, great. Very quick conclusion. So I hope I've somewhat convinced you that blind radio searches are promising, that we're finding distinct TDEs, and hopefully with more work, we'll actually be able to say a little bit more about what's producing the radio emission, what's different about these events from the optically selected and X-ray selected TDEs. And of course, there's a lot of work to do, so we're actively working on expanding the optical selection, pushing to dustier TDEs, for example. And I would love to talk to people about what you want to see for expanding optical selections of TDEs. We're also working on simple analyses of the expected multi-wavelength emission as you change, say, the amount of dust or the structure of the dust in the nuclear region. And I would love to see more systematic radio follow-up of TDEs, particularly as we expand the optical sample, trying to push to the weirder events. Thank you.
All right, thank you so much for the great talk. I'm curious, have you proposed for JWST follow-up of your host list transient?
We did not get it, unfortunately, but if anyone here is involved in that process, I'd love sometime, yeah. Even with JWST, if we get lucky and detect the host and we see it's off nuclear or nuclear, I think it's somewhat suggestive. It's surprisingly hard to say much about it, though, with just one radio data point and maybe one detection of the host. But yeah, I'm hoping that, I think the best way to go after things like this is instead to use future radio surveys to find more of them, like the SA 2000 might push on them. So it hints at what we might find in the future and hopefully can constrain better. But yeah.
Cool. All right, let's start with Yvette on this side.
Hi, this is really cool. Thank you. So I was just wondering, for all your ones with the lack of multi-wavelength components, and obviously dust plays a role into that, are there any other reasons you've considered on why you might not have emission that don't have to do with dust?
Yeah, so I mean, I think there are a number of models for TDEs where you might not expect an optical flare at all. Like I think Windman had some papers where for low mass black holes, you might not be able to launch some of the reprocessing layers to produce optical emission. And so I think there's definitely a number of other possibilities where if we could try to measure some correlations between like radioluminosity and X-ray limits and optical limits, we'll probably be able to get at that. I just like the dust explanation because we're seeing these optically selected events that are cool and faint and have long-lived sort of intermediate with spectral features, but there's definitely other explanations for sure.
Cool, thanks.
Let's go across the room.
Hi, Megan Newsom again, grad student here. You mentioned there's like a sample of 30 plus that you're getting spectra actively reduced right now. Can we get a teaser or maybe your expectations of what's in them? Like, I know you said you were doing it to rule out AGN, but in that process, might you see coronal lines or other interaction signatures in them?
Yeah, so far I think from all the ones I've looked at, I haven't seen any with coronal lines that don't also have like multi-wavelength counterparts. I haven't set very deep limits or anything. This is just sort of what I'm remembering by eye, which is sort of interesting in itself, for sure. Yeah, I don't remember seeing much else interesting. It's mostly host galaxy emission. Yeah.
Thank you.
Johan?
So for the sixth event where you do have optical flares, if you infer the radio launch time, are they also consistent with the first optical rise?
Yeah, no, not really. So one thing is a lot of our radio flares are very clearly multi-component. Like we don't just have a nice synchrotron turnover. We see bumps, things like that. So it's sort of hard to piece out what is like are they two different outflows, or can you fit them as like one thing hitting multiple components of the circumnuclear medium. But in general, I don't see any clear trend for radius going back to the time of the optical flare. Of course, some of the ones that overlap between our samples, yes. But yeah, so it's possible that maybe one of the components you could trace back to the optical, but there's degeneracies in fitting them, and it's also not clear exactly what's producing the multiple components, so it's a little hard to say.
Elena?
Hi, so thank you very much for the clarity with which you explained the various techniques to discover radio TD. And it seems to me that the blind radio searches are better, you could have a better handle on rates for radio TDs. Do you already are you working towards that? Do you already have a number for us?
Yeah, no, that's definitely a long-term goal. I don't have a number for the full sample. I mean, I could say for the radio plus optical TDEs, which I think are the most reliable of our sample, we're seeing similar rates to what you all are seeing. So it's like greater than 30% of the optical TDEs have radio emission. For the full sample, I expect the rate to be quite a bit higher, but I haven't actually computed it yet. So hopefully in the next year or so, we'll get to that paper and I'll be able to give you an actual answer.
Okay, thanks.
Thank you for a great talk. So I'm obsessed with recoiling black holes, like recoiling supermassive black holes. So I was like really cool to see like a hostless TDE candidate. I was wondering if you could say a few more words about where that's going. If there's like surveys to try to look for more of these hostless TDEs or anything like that.
Yeah. So there are definitely a lot of different avenues you could take. Like upcoming surveys will be really good. What we're currently doing is, I think, trying to push the bounds with ZTF. So trying to push the bounds of what a TDE is. So in particular, I'm already leading a hostless TDE search. We haven't found anything, but just looking for any ZTF flare that doesn't have a galaxy associated with it that sort of looks like a TDE. We're also working on just an off-nuclear TDE search. So looking for TDEs that are, maybe 10 kiloparsecs from their host galaxy. Again, that's more of a work in progress. Haven't found anything definite yet. We are finding candidates for sure though. But if there's anything in particular you want to see, come talk to me. We can make it happen.
Sweet, thank you.
So I have a question about the host list here, hostless TDE. Is the limit on the host coming only from the optical and nothing from IR?
No, so we have taken every single image of the cosmos field at that position and looked at it. So this includes lots of IR, basically every wavelength you can think of. There's an image of the cosmos field. It's one of the best studied fields of like all time. So we can say there's, to the depth that this field has been observed in the IR, there's no host there. It's not the deep. I mean, it's deeper relative to what you see elsewhere in the sky, but the constraints aren't that deep. I can show you plots afterwards of sort of limits on IR emission, but yeah, so there's no evidence for a host at any wavelength that we've got data for.
So it's probably not a dust obscured galaxy either.
It could be a dusty galaxy. Let's see, I might actually have a plot in the backup. Yeah, so here we go. So this plot is showing for a old stellar population, so the age of the universe at a given redshift, what limit on stellar mass we can set given all of the observations of the field, including IR, with a range of extinctions allowed. And so if you put it at high enough redshift and make it dusty, you can get like a Milky Way mass galaxy and not be able to see it in current observations. Sorry, I keep hitting the wrong button. But yeah, it would still have to be a fairly small galaxy, I think, or like ridiculously extincted.
Thank you.
All right, Decker, were you next? Or?
Yeah, thanks. I was also going to ask about this hostess thing. This is super interesting. And thinking also about the idea that it could be some sort of high redshift submillimeter galaxy. Do you have any constraints from like the radio SED that suggest that it's unusual because of an underlying host, or do you have any ALMA constraints or anything like that?
So we don't have a radio SED. We have a single radio detection at one frequency, and that's it. So we can't really say anything based on that, unfortunately. Yeah, and it's so faint even at its brightest that getting more observations of the field would take a long time, so we haven't pursued much follow-up. So yeah, I think the best avenue, as I said before, to finding out more about what this kind of thing is finding more of them in future surveys. Yeah,
awesome. Thanks.
And Muriel, I think we have time for your question, and then we'll go to the coffee break.
Yeah, thanks for a great talk. For the sources that you don't have the optical or X-ray counterpart, how you define the T-star that you're using the X-axis?
Yeah, so that's sort of, let's see it.
Yeah, like that for the X-axis for those of you who don't have.
For a lot of these is extrapolated the radio emission back and just assumed that was T-star, which of course is not going to be quite correct. But a lot of these are like a decade old anyway, so their position's not going to shift that much, even if you change the start date by a year. But yeah, it's quite uncertain for all of these. Yeah.
Thanks.
But yeah, generally extrapolations back.
All right, let's thank all three of our speakers again. And we'll reconvene for part 2 after the coffee break. Don't see anyone leaping up for other logistical announcements, so see you back in, I believe, 20 minutes, half an hour?